So in this video, we're going to continue our physical chemistry lecture series. For those of you guys who are future physical chemists or are interested in the field of physical chemistry. So let's continue with our discussion from lecture 3. Right. So now we're going to talk about the average kinetic energy. The average kinetic energy of a particle. So we know that, and this is taking you back to physics, that our kinetic energy Ke is equal to 1/2 mass times velocity squared. Again, this is a kinetic energy. This is a kinetic energy of a single molecule with speed v. Right. So then we say that the average kinetic energy Ke of a single gas molecule. So if we apply it to a single gas molecule, we'll say that the average kinetic energy, and we put our arrows or brackets, is equal to 1/2 mv squared. Right? Remember, we're saying physical chemistry. Anytime we see all those brackets, that means average. So then, if we say the mass, we could then say the mass of a molecule m. Right? So the molecule m. So the mass of a molecule m is constant. So in other words, the average kinetic energy should be equal to 1/2 m, since that's constant, v squared. So the only thing we did was factor the constant out, since m now is a constant. We factored 1/2 and the m out of the equation times v. Now we learned about the average kinetic energy in lecture 3. And so we could say this like, we could say, okay, well, from before, we know that an average velocity squared is equal to 3RT over m times NA, where NA is actually our Avogadro's number. So then we can essentially say that the average kinetic energy from this formula is equal to 1/2 m times 3RT over m times NA, which would be NA, again, would be your Avogadro's number. So again, if we simplify the equation with our m and m canceling out each other, then we simply get, in other words, our average kinetic energy is going to be equal to 3RT over 2 NA. Again, where NA would be Avogadro's number. And we say this is for a single gas molecule, right? So this is important in physical chemistry, this equation of the average kinetic energy. We could apply the same principle for 1 mole of gas molecules, right? So this would be for 1 mole of gas molecules, right? So if we apply the principles for 1 mole of gas molecules, let me erase this. Right, but if we apply the principles for 1 mole of gas molecules, then we're essentially saying that the average kinetic energy is equal to NA, which is Avogadro's number, times 3RT over 2 NA. Right? Again, you could quickly realize here that the NAs would cancel and give us the equation above. Or we could actually simplify this and say, okay, well, the average kinetic energy is equal to 3/2 RT, right? If we simplify our equation. And so this is the important formula you need to know for the average kinetic energy of 1 mole of gas, right? So this would be the average kinetic energy of 1 mole of gas molecules at temperature T. So that equation is important for a single mole for 1 mole of gas molecule at temperature T. So in other words, if we do an example, we could say that, okay, well, at room temperature, right, which is 25 degrees C, the average kinetic energy we could actually calculate. So the average kinetic energy in this case would be average KE is equal to 3/2 RT, which is equal to 3/2 R, which in this case would be 8.314, which is the ideal gas constant, times 298. So I made a mistake here, but times 298.15 kelvins, and that's equal to approximately about 3720 joules, or 3,720 joules, which is approximately about 4 kilojoules per mole. So in other words, we're saying that this energy, which can be thought of as thermal energy contained in a gas, is readily available for overcoming internal rotational energy barriers, or even activation energy barriers for chemical reactions. Right. So for comparison, we could say that the internal rotational barrier in ethane is about 12 kilojoules per mole. Right? This is low enough that at room temperature, considerable rotation occurs around the CC double bond in the ethane molecule. So for a molecule of ethane, right, we say that the internal rotational energy, or the average kinetic energy, is about 12 kilojoules per mole. And so because it's about 12 kilojoules per mole, it is actually low enough that at room temperature, we actually have rotation around the carbon-carbon single bond in ethane. So we have rotation around the carbon-carbon single bond in ethane, right? And this is the bond we're really talking about. So we have some sort of rotation around that carbon-carbon bond in ethane, right? So this is what the average kinetic energy can tell us about a particular molecule. Let's switch gears to the speed of gas molecules. So let's look at the speed of gas molecules. The first one we want to look at is the root mean squared speed. So what is the root mean squared speed, and the formula? So RMS, which stands for root mean squared speed, right? So the RMS speed is equivalent to the square root of the average velocity squared. That is the formula by definition. Or in other words, this is equal to the average velocity squared raised to the 1/2 power. Now, if we go back to the lecture from before, or not even the lecture from before, but just above in this lecture, we said that the average velocity squared is equal to 3RT over m times Na, where m is the number of molecules. And this is essentially equal to 3RT over big M. Now, big M replaces m times Na, which is essentially the molar mass of the molecule, or the molecular weight, right, of the gas molecule. So that's what big M stands for. So knowing this, we can then say that the root mean square speed, or the RMS speed, is therefore V sub RMS. That is equal to, then we're plugging in, that is equal to then the square root of 3RT over big M, which would be our molar mass. So that is the equation for the root mean square speed. The second one we want to look at is the average speed. And this comes from the probability distribution function, which we spoke about in the last lecture. Right. So from the properties of probability distribution function, we say that the average speed, or V average, is equal to the integral from 0 to infinity of V times f of V dV. This is an integral from 0 to infinity, right? Where we did say that f of V is the Maxwell-Boltzmann distribution function, right? So we did say in this integral that f of V is the Maxwell-Boltzmann distribution function. And this is the function, the Maxwell-Boltzmann distribution function. F of V is equal to 4 over the square root of pi times m over 2kb, where kb is a Boltzmann constant, times T, the temperature, raised to the 3/3, or 3/2 power, times V squared raised to the exponent, and this is all raised to the exponent, minus m times V squared over 2kb, which is Boltzmann constant, times the temperature. So this is where the average square speed is derived from. So then if we break this down furtherly, we can say that the average of V is equal to all these constants, 4 over pi, or in other words 4 over the square root of pi, times m over 2 kbt raised to the 3/2 power. And we factor that out of the integral from 0 to positive infinity of v cubed times the exponent. Because remember, we had an original v, so we're multiplying that together, will give us from v squared to v cubed times the exponent, and everything in the exponent becomes negative mv squared over 2kbt dv. And then kb again is our Boltzmann constant. Now this is a tough integral, and so if we do the integral, and so essentially we're doing the integral from the integral tables. So you could get these integrals from tables within various mathematical integral books. And so essentially we take the integral from 0 to positive infinity of v cubed raised to the exponent now negative av squared dv, and that is equal to 1 over 2a squared. Now in our case, when we took the integral, in our case a, this constant a, is actually equal to m over 2k bt. So if we continue our mathematical endeavors, we actually get the average of v is equivalent to 4 over the square root of pi times m over 2kbt raised to the 3/2 power, all being multiplied by 1 over 2 times m over 2kbt raised to the 2nd power. And so if we actually go through a simplification, we actually get the average of v is equal to the square root of 8 kbt over pi m. So that's just doing a bunch of mathematical operations to simplify the equation. Now remember that last lecture, in lecture 3, we said that the Boltzmann constant is really equivalent to the ideal gas constant R divided by Na, which is Avogadro's number. So that's really what Kb is in the equation. So in other words, we could substitute that for Kb in the equation. So therefore, the average velocity V becomes, or the average speed becomes 8RT divided by pi m Na. So all I did was substitute Kb, substitute R over Na for Kb. Or I could actually write this in a different way. We could actually say the average speed, or the average velocity, is equal to the square root of 8RT over pi big M, where M is the molar mass. Okay. So that's the equation for the average speed. Third one we wanted to talk about was the most probable speed. The third speed we want to talk about is the most probable speed. So this is actually the speed for which f of v is pretty much a maximum. In other words, when f of v is equal, when f prime of v is equal to 0, right? So again, let's say that again. The most probable speed is the speed for which the function f of v is a maximum. In other words, we're really saying that this is when f prime, or the derivative of f of v, is equal to 0. So that's all we're saying. Now, if we remember, because we just spoke about it, remember that the Maxwell Boltzmann, I'm just going to write this function. I'm just going to write distribution for distr for distribution. Remember that the Maxwell Boltzmann distribution function is, we did say that this was f of v is equivalent to 4 divided by the square root of pi times m over 2kb t raised to the 3/2 power, all be multiplied by v squared, and all this is raised to the exponent negative mv squared over 2kb t. So that is a Maxwell distribution function, again, for your memory. Now the reason why I wrote this function out again is because it has a specific form. So this function that has the form f of v is equivalent to c, some constant c, times v squared e raised to the negative av squared. So that is the general form of the function. Now, to differentiate this form of the function, we actually use the product and the chain rule, right? So this is from your calculus class. Right? So to differentiate a function of this form, and really I'm talking about the form above, we actually have to use the product rule and we actually have to use the product rule and the chain rule. So we're not going to revisit that in this class, but you should be very aware of the product and chain rule. So if I go straight to derivatives, then I say f prime of v, this is equivalent to c times d dv v squared times e negative av squared, and then I'm going to simply add that times v squared. So I'm going to add v squared now, plus I'm going to multiply this by d dv of e negative AV squared. And so this is your product rule from Calculus 1. Right? So that is the product rule. And then by the chain rule, we essentially get C times now 2 VE raised to the negative AV squared plus V squared times E raised to the negative AV squared. Right? And that's being multiplied by negative 2 AV. And this is the chain rule. So if we simplify this, essentially we have 2 CVE raised to the negative V squared times 1 minus AV squared. So the only thing I did there was simplify. Now, when is actually the derivative of f of v, the function f of v is equal to 0? When? That's an important question to ask. Right? So when does it actually equal to 0? Well, we actually have to use a graph to explain this. So we did say that 2CVE raised to the negative AV squared, this is actually equal to 0 when v is actually equal to 0. And I'm going to explain this on the graph below, right? But it's actually, it must, so 2CVE raised to the negative AV squared must be equal to 0 when v is equal to 0, since, and this must be true, since e raised to the negative AV squared cannot equal to 0 for any of the values of v. All right, so we say that the derivative of function must be equal to 0 when v is equal to 0, since the exponent, in this case e raised to the negative AV squared, cannot be equal to 0 for any of the value of the functions of v. Right? So if we look at a graph, what I'm essentially saying is that on the x-axis I have v, on the y-axis I have f of v, and around this portion is where f prime of v is equal to 0. Right? Right in this circle is where about f prime of v is equivalent to 0. So this is what we actually call a minimum representation of f of v. So if we go back to my whiteboard, we say that this represents the minimum of f of v. So that circle right there represents the minimum of f of v. Now, we also should make note of something else. 1 minus AV squared is equal to 0, but that is equal to 0 when AV squared is equal to 1, or in other words, V squared is equal to 1 over A. In other words, V squared is equal to 1 over A. So this part of the formula we're tackling. All right. So we did say that 1 minus AV squared is equal to 0 when AV squared is equal to 1, or V squared is equal to 1 over A, or V is equal to 1 over the square root of A. These are all equivalent. This actually represents the maximum of f of v, right? And again, another graph to illustrate what we're talking about here. right? So I have v on the x-axis, I have f of v on the y-axis. Again, here's my function, and again, this represents the maximum. So, continuing on what we had learned previously, we had previously called A, and that is equivalent to 2b. I'm sorry, 2kb. Right, so that is equivalent to m divided by 2kb t. So in other words, so the most probable speed is vmp, which is most probable, is then therefore equal to the square root of 2kb times t over m, where kb is the Boltzmann constant. Again, we can actually simplify this. So if we use kb is equal to, again, r divided by na, where na is Avogadro's number, and m is equal to m times na, right? So the molar mass is equal to the number of molecules times Avogadro's number, then we really get vmp, simplifying it, to be equal to the square root of 2 RT over the molar mass, which is m. So let's represent all these three speeds on a graph. Right? I have a graph where on the x-axis I have speed, the y-axis I have f of v. And again, I have my bell curve distribution. What would you actually see? Just in the middle, this would actually be our most probable speed. The average speed would be just above that, and this would be v average. And then the root mean square speed would be just above that, Vrms. So this is how the three speeds are on a graph. And we're going to do an example. Right? So some comments with respect to the graph. Right? So for a narrow distribution, the speeds are actually similar. So for a narrow distribution, the speeds are actually very similar. Right? Now, the most probable speed, Vmp, is actually approximately about 80% of the root mean square speed, Rms. And the average speed is actually approximately 90% of the root mean square speed, right? So those are some comments with respect to the graph. The last one we want to note is that all speeds are independent of pressure and volume of the gas. So that's very important. The last one, which I'm not going to write, is that all speeds are actually independent of the pressure and volume of the gas. So let's look at an example. For a nitrogen molecules, or for nitrogen molecules, so not for A, but for nitrogen molecules at room temperature, again 25 degrees C, we want to calculate the root mean square speed, the average speed, and the most probable speed. So we're going to calculate average speed, Vrms, and Vmp. How do we do it? Let's start with the root mean square speed first. Right? Going back to our lecture, we know that Vrms is equivalent to the square root of 3RT divided by big M, which is the molar mass. Right? So therefore, essentially we're substituting, right? So again, what are the numbers we need? We know that R is equivalent to 8.314 joules Kelvin inverse mole inverse. We know that T is our temperature, which is equivalent to now 25 degrees C plus 273.15, and that is equal to 298.15 kelvins. We know that M, which is the molar mass, because we're dealing with nitrogen gas molecules, it's N2, so we're really looking at 28.02 grams per mole. Now, the molar mass, we have to keep them in SI units. And so the molar mass for these equations, you have to remember that they're equivalent, it must be in kilograms per mole. So that is important, that the molar mass must be in kilograms per mole. So if we convert 28.02 grams per mole, what we're looking at is 28.02 times 10 to the negative 3 kilograms per mole, right? So it must be in kilograms per mole. So therefore, if we just substitute the numbers into the equation, what we really get is that for Vrms, this is equivalent to the square root of 3 times 8.314 times 298.15 divided by the molar mass, which would be 28.02 times 10 to the negative 3, and that is equivalent to about 515 or 515 meters per second. If you look at B to calculate the average speed, we did say that the average speed, the equation of the average velocity, is equal to the square root of 8RT divided by pi big M. Right? So all we're doing again is substituting, and if we substitute our numbers, 8 times 8.314 times the temperature 298.15 divided by pi, we know that's a specific number, and this is times 28.02 times 10 to the negative 3. And so we get the average speed about 475 meters per second. The last one we want to calculate is the most probable speed. And we know that Vmp is equivalent to the square root of 2RT over big M, again, which is our molar mass in kilojoules per mole. So this is equal to, plugging in our numbers, this is 2 times 8.314 times 298, so you times 298.15 divided by 28.02 times 10 to the negative 3, and this is equivalent to about 421 meters per second. And this is it for lecture 4.